At the center of the Milky Way lies something 4 million times the mass of our Sun, warping space and time around it. Light that comes too close, within 12 million kilometers, is trapped, unable to escape. This region, defined by the event horizon, separates the universe from what happens beyond. Known as Sagittarius A, it is a supermassive black hole. Black holes occupy the places where the most massive stars once burned brightly, found at the centers of galaxies and on the boundaries of our understanding. They form naturally, the inevitable result of gravity when too much matter collapses into an extremely small space. Yet, while the laws of nature predict their existence, they cannot fully explain them. Gravity is a quiet but relentless force, always pulling, always attracting, and never stopping. It is even pulling you right now, trying to drag you through the floor toward the center of the Earth. But the ground pushes back, and everything stays in place because of the structure of matter itself. Matter feels solid, but it is mostly empty space. Atoms, made up of tiny nuclei surrounded by electron clouds, create the illusion of solidity. These electron clouds keep atoms from getting too close, and this repulsion is what stops you from sinking through the floor. This same force is powerful enough to stabilize dying stars, even those up to twice the mass of the Sun. However, beyond that limit, gravity takes over completely, and that is where neutron stars are formed. The surface of a neutron star is a place of unimaginable force, with gravity 100 billion times stronger than on Earth. Anything that falls onto it is instantly crushed and turned into a dense soup of nucleons. If you were to fall onto a neutron star, the atoms that make up your body would be compressed into neutrons, packed so tightly they would move at nearly the speed of light as they jostle for space. This frantic motion is enough to support a neutron star with a mass of up to 2 suns. But there is a limit. Add just a little more mass, and gravity takes over completely. The city-sized star would collapse, creating a singularity in spacetime. One cosmologist described the Big Bang singularity as a day without a yesterday. A singularity born from gravitational collapse is its opposite, a moment with no tomorrow. All that remains is a dark shadow of what once was, a black hole. Let's dive into the video to explore what happens when a star collapses into a black hole and the mysteries that lie beyond the event horizon. Spacetime and black holes. For centuries, our understanding of the universe was built on the foundations laid by Isaac Newton, who viewed space and time as separate, unchanging entities. Space was a vast, static stage where the drama of the cosmos unfolded, and time was an ever-flowing river that ticked uniformly for all observers. This view, intuitive and practical for everyday experiences, stood unchallenged for over 2 centuries. However, in 1905, Albert Einstein transformed our perception of reality with his groundbreaking theory of relativity, weaving space and time into a single entity: spacetime. The seeds of spacetime unification were planted when Einstein grappled with a puzzling feature of light. James Clerk Maxwell's equations, which describe electromagnetic waves, revealed that the speed of light in a vacuum is constant, regardless of the motion of its source or the observer. This was fundamentally at odds with the Newtonian idea of relative motion. For example, if you are running toward a sound source, the sound waves seem to reach you faster. Yet, light behaves differently. It maintains its speed no matter how fast you move. Einstein resolved this paradox by rethinking the very fabric of reality. He proposed that measurements of time and space are not absolute but depend on the observer's relative motion. To preserve the constancy of light speed, time and space must stretch, compress, and shift. This realization became the cornerstone of his special theory of relativity. One of the most astonishing consequences of Einstein's theory is the relativity of time. Imagine a spaceship traveling at a significant fraction of the speed of light. To an outside observer, the clock on the spaceship ticks more slowly compared to their own, a phenomenon called time dilation. This is not merely a trick of perception but a measurable reality, as confirmed by experiments like the Hafele-Keating experiment in 1971. Atomic clocks were flown around the world on commercial jets. When compared to stationary clocks on Earth, the airborne clocks recorded different times, precisely as Einstein predicted. Space also behaves in unexpected ways. Length contraction, another relativistic effect, means that objects moving at high speeds appear shorter along their direction of motion to an outside observer. For instance, particles traveling close to the speed of light in the Large Hadron Collider perceive the 27-kilometer ring as being only a few meters long. These effects reveal that time and space are not rigid and universal. Instead, they are intertwined and malleable, forming a four-dimensional fabric known as spacetime. To understand spacetime, we must think of events, things that happen, as points within this four-dimensional continuum. For example, an astronaut stepping onto the moon is not merely at a place, the moon, but also at a moment in time. These coordinates in space and time are inseparable and collectively form spacetime. Einstein's genius lay in showing that the separation between events depends on the observer. However, he also discovered something remarkable. Despite this variability, there is one quantity all observers agree upon: the spacetime interval. This invariant combines spatial and temporal separations into a single, unchanging measure, reflecting the deep interconnectedness of space and time. Special relativity describes a universe without gravity, where spacetime is flat and unchanging. But Einstein knew this was only part of the story. His next leap came with the General Theory of Relativity, published in 1915. Here he introduced the idea that spacetime is not static but can curve and warp under the influence of mass and energy. Think of spacetime as a rubber sheet. When you place a heavy object like a bowling ball on the sheet, it creates a dent. Smaller objects rolling nearby will follow curved paths, not because of a mysterious force pulling them, but because the sheet itself is distorted. Similarly, massive objects like stars and planets bend the fabric of spacetime, guiding the paths of nearby objects. This is the essence of gravity in Einstein's framework. Not a force, but the geometry of spacetime itself. The implications of curved spacetime are profound. Light, which always travels in straight lines in flat spacetime, follows curved paths near massive objects, leading to phenomena like gravitational lensing, where the light from distant stars and galaxies is bent around intervening masses, creating stunning arcs and rings in the sky. Einstein's equations also revealed that time flows more slowly in stronger gravitational fields, a phenomenon known as gravitational time dilation. This effect has been experimentally verified by placing precise atomic clocks at different altitudes. Clocks closer to Earth's surface, where gravity is stronger, tick more slowly compared to those at higher altitudes. For everyday life, this difference is minuscule, but it becomes critical in technologies like GPS, where accounting for time dilation ensures the system's accuracy. Nowhere is the unification of space and time more dramatic than near black holes. These enigmatic objects warp spacetime so severely that not even light can escape their grasp. The event horizon, a black hole's boundary, represents a point of no return, where spacetime curvature becomes infinite. Beyond this horizon, time and space as we understand them cease to exist. For an external observer, an astronaut falling toward a black hole appears to slow down, their time stretching infinitely as they approach the event horizon. To the astronaut, however, time continues normally as they plunge into the unknown. This bizarre behavior arises from the extreme warping of spacetime, a direct consequence of Einstein's equations. Spacetime is not merely a backdrop but an active participant in the dynamics of the universe. It governs the motion of planets, the behavior of light, and the evolution of galaxies. The ripples in spacetime, known as gravitational waves, were first predicted by Einstein and later detected by the LIGO experiment in 2015. These waves, generated by colossal events like black hole mergers, carry information about their origins, opening a new window into the universe. Einstein's unification of space and time marked a profound philosophical shift. It challenged our intuitive notions of reality, replacing them with a vision where the universe is a dynamic, interconnected whole. Time is no longer an absolute tick of a cosmic clock, and space is not a static grid. Instead, they form a fluid tapestry shaped by mass, energy, and motion. This new understanding extends to the very fabric of existence. The holographic principle, inspired by black hole physics, suggests that spacetime itself may be an emergent phenomenon arising from deeper quantum mechanical principles. Such ideas push the boundaries of modern physics, hinting at a reality even stranger than Einstein imagined. Gravity's curved fabric. Imagined in 1916, just a year after Albert Einstein introduced his general theory of relativity, Karl Schwarzschild provided the first exact solution to Einstein's equations. This groundbreaking work described the geometry of spacetime around a spherical, non-rotating star. Schwarzschild's solution went on to reveal some of the most fascinating phenomena in physics, including the concept of black holes, although the term itself was not introduced until decades later. At its core, Einstein's general relativity reshaped our understanding of gravity. It described gravity not as a force, as Isaac Newton had proposed, but as a curvature in the fabric of spacetime caused by the presence of mass and energy. To understand this, imagine spacetime as a flexible sheet. When you place a heavy object like a bowling ball on the sheet, it causes the surface to bend. Smaller objects placed nearby naturally roll toward the heavy one, not because the larger object is pulling them, but because they are following the curve of the sheet. Schwarzschild's solution mathematically formalized this bending. He showed that spacetime around a massive object is not flat but curved. The degree of curvature depends on the object's mass. For smaller objects like the Earth, this curvature is gentle. But for extremely massive objects like black holes, the curvature becomes so extreme that it creates a boundary from which not even light can escape. In general relativity, the curvature of spacetime is described using a mathematical framework called the metric. The metric is essentially a tool that relates the coordinates of spacetime to the actual distances and times experienced by objects within it. In flat space, such as a tabletop, the metric is simple. It reflects the familiar Pythagorean theorem, where the distance between 2 points is calculated based on their positions. In curved spacetime, the metric becomes more complex because it must account for the bending of space and the dilation of time caused by gravity. Schwarzschild's metric was the first to describe how this works near a spherical mass. It provided a way to calculate how distances and times are stretched or compressed due to the presence of a massive object. To visualize spacetime curvature, think about the surface of the Earth. Although the Earth is round, small areas like a football field appear flat to us. Mathematically, you can describe distances on these small patches using flat geometry. But as you consider larger areas, the curvature of the Earth becomes apparent. The same principle applies to spacetime. While spacetime may appear flat in small regions, its curvature is evident over larger scales or near massive objects like stars and black holes. Schwarzschild's metric takes this idea further. It reveals that spacetime is stretched not only in space but also in time near a massive object. Time itself slows down relative to regions farther away. This phenomenon is called gravitational time dilation. For instance, a clock positioned near the surface of a massive star ticks more slowly than a clock far from it. Schwarzschild's solution introduced a critical concept: the Schwarzschild radius. This radius defines the size of a region around a massive object where the curvature of spacetime becomes so extreme that nothing, not even light, can escape. This boundary is known as the event horizon. For an object like the Sun, if it were compressed into a sphere with a radius of about 3 kilometers, it would become a black hole with its event horizon defined by the Schwarzschild radius. The event horizon is not a physical surface but a point of no return. Anything crossing this boundary is irrevocably drawn toward the singularity, a point where spacetime curvature becomes infinite. Inside this region, our understanding of physics breaks down. Schwarzschild's solution initially described the spacetime around stars, but it also laid the groundwork for understanding black holes. By stripping away the matter within the Schwarzschild radius, what remains is a pure black hole, a region of spacetime defined entirely by its geometry. The curvature in this region is so severe that it creates a singularity at the center where the density of matter and the strength of gravity become infinite. Time and space are profoundly affected near a black hole. An outside observer watching an object fall toward the event horizon would see the object slow down as it approaches the boundary. Time for the object appears to freeze as it reaches the event horizon. For the object itself, time continues as normal, and it crosses the horizon without noticing any dramatic change. The warping of spacetime has observable consequences. One of these is gravitational lensing, where light passing near a massive object is bent, creating distorted or duplicated images of distant stars and galaxies. This effect is commonly observed around massive galaxy clusters and provides valuable insights into the distribution of matter, including dark matter in the universe. Another effect is the slowing of time near massive objects, as seen in experiments with GPS satellites orbiting Earth. These satellites experience slightly weaker gravity than we do on the ground, so their onboard clocks tick faster. Engineers must account for this time dilation to ensure accurate navigation data. While Schwarzschild's metric describes the spacetime around a spherical mass, it is essential to distinguish between local and global effects. Locally, spacetime may appear flat, and objects follow straight-line paths called geodesics. Globally, these geodesics reveal the curvature of spacetime, bending toward massive objects. This distinction helps explain why astronauts aboard the International Space Station feel weightless. They are in free fall, following a geodesic through the curved spacetime created by Earth. Though they experience no force, their path is continuously bent toward the planet, keeping them in orbit. Einstein's general relativity is remarkable because it applies universally. From small-scale interactions near planets to the vast cosmic distances between galaxies. Schwarzschild's solution is just one of many metrics that describe specific scenarios, but it set the stage for understanding more complex phenomena, including rotating black holes known as Kerr black holes and charged black holes known as Reissner-Nordstrom black holes. General relativity also predicts phenomena like gravitational waves, ripples in spacetime caused by accelerating masses. These waves were first directly observed in 2015 by the LIGO experiment, confirming yet another of Einstein's predictions. One of the most counterintuitive aspects of general relativity is the interplay between time and space near a black hole. Both are stretched to their limits. For someone falling into a black hole, time appears normal from their perspective. But to a distant observer, their motion slows to a standstill. This apparent contradiction arises because time and space are not fixed but are part of the same dynamic fabric influenced by gravity. The concept of geodesics helps clarify this. Objects move along the shortest paths in spacetime. But in curved spacetime, these paths are not straight. A light beam near a massive object bends because its geodesic is curved, not because it is acted upon by a force. The understanding of curved spacetime is not just theoretical. It has practical applications in technologies like GPS, which rely on precise timing and positioning. By accounting for the effects of general relativity, scientists and engineers ensure these systems function accurately. Furthermore, studying the warping of spacetime offers insights into the universe's history and structure. The cosmic microwave background, for example, shows how the distribution of matter has shaped spacetime over billions of years. The Kerr black hole. In 1963, mathematician Roy Kerr discovered a solution to Einstein's equations that described a spinning black hole. This model introduced a more complex geometry than the non-rotating Schwarzschild black hole. Spinning black holes, now called Kerr black holes, possess unique structures and behaviors, transforming the way we understand spacetime around such objects. These black holes, characterized by their rotation, reveal phenomena that challenge conventional ideas about space, time, and energy. Kerr black holes are defined by their spin, which influences their structure. Unlike Schwarzschild black holes, they are not perfectly spherical. Their rotation causes them to bulge at the equator, forming an oblate shape. This distortion of spacetime gives rise to several key regions. Kerr black holes have two event horizons instead of one. The outer event horizon marks the point beyond which nothing can escape the gravitational pull of the black hole. The inner event horizon lies closer to the singularity and separates a region of different spacetime dynamics. Surrounding the outer event horizon is the ergosphere, a region where spacetime is dragged along by the black hole's spin. Objects within the ergosphere cannot remain stationary relative to a distant observer. Instead, they are compelled to move in the direction of the black hole's rotation. At the core of a Kerr black hole lies the singularity. But unlike the point singularity of Schwarzschild black holes, the Kerr singularity takes the form of a ring. This ring is positioned in the equatorial plane and is surrounded by spacetime distortions that defy simple descriptions. The rotation of a Kerr black hole creates a phenomenon known as frame dragging. Space-time around the black hole is twisted in the direction of its spin, an effect that grows stronger closer to the ergosphere. Frame dragging has profound implications for the behavior of matter and energy in the black hole's vicinity. In the ergosphere, the dragging of spacetime is so intense that nothing can resist moving in the direction of the black hole's spin. Even light is compelled to follow this rotational flow, though particles and objects can still escape the ergosphere under the right conditions. Frame dragging facilitates processes that extract energy from the black hole. One such process is the Penrose process, which occurs within the ergosphere and allows particles to gain energy by interacting with the black hole's rotation. The Penrose process is a theoretical mechanism proposed to extract rotational energy from a Kerr black hole, exploiting the unique properties of its ergosphere. The ergosphere is a region outside the event horizon where spacetime is dragged by the black hole's rotation, allowing particles to achieve negative energy states relative to distant observers. In this process, a particle enters the ergosphere and splits into two fragments. One fragment is propelled into the black hole, carrying negative energy, while the other escapes with more energy than the original particle possessed. This ingenious mechanism illustrates how energy could theoretically be siphoned from a rotating black hole's spin. The structure of spacetime within a Kerr black hole undergoes remarkable changes, especially in the region between its two event horizons. These horizons, the outer and inner boundaries, delineate distinct areas with unique properties. In the space between the horizons, the behavior of spacetime becomes highly unusual. Time-like paths are inexorably directed toward the inner horizon, rendering escape impossible for anything that crosses into this intermediate zone. Beyond the inner horizon lies the core region of the Kerr black hole where the singularity resides. Unlike the point singularity of a Schwarzschild black hole, the Kerr singularity takes the form of a ring. This ring singularity introduces possibilities for paths through spacetime that are entirely absent in non-rotating black holes, hinting at fascinating and theoretical prospects for exploring the extreme environments shaped by the intense rotation and curvature of spacetime. The ring singularity of a Kerr black hole represents a departure from the idea of singularity as points. This ring structure is surrounded by a region of spacetime that exhibits exotic properties. The unique geometry of the Kerr singularity suggests that it may not necessarily terminate all paths. Instead, certain trajectories could bypass the singularity entirely, offering theoretical routes to other regions of spacetime. Theoretical extensions of the Kerr spacetime propose that the black hole may connect to other universes. These connections appear as pathways within the black hole's inner regions, leading to speculation about the existence of an infinite number of interconnected universes. If a Kerr black hole spins faster than a critical limit, its event horizons disappear, exposing the singularity. This state, called a naked singularity, defies the typical structure of black holes. Naked singularities are not shielded by an event horizon, meaning their effects could influence distant regions of spacetime. They represent a breakdown in the predictive nature of physical laws as their behavior is no longer hidden. To address the potential chaos introduced by naked singularities, physicists have proposed the cosmic censorship conjecture, which asserts that naked singularities cannot naturally form in the universe. This conjecture remains unproven but highlights the theoretical tension surrounding these objects. The ergosphere of a Kerr black hole is a region of spacetime where negative energy states can exist. These states arise from the interplay between the black hole's rotation and the properties of spacetime. In the ergosphere, particles within the ergosphere can acquire negative energy relative to observers at infinity. This unique property makes the ergosphere a site for energy transfer and exotic physical processes. The existence of negative energy states in the ergosphere challenges our understanding of energy conservation and highlights the intricate dynamics of rotating black holes. Detecting and studying Kerr black holes is an ongoing challenge in astrophysics. While their effects can be inferred from observations of nearby matter and light, direct detection is impossible due to the nature of black holes. Kerr black holes influence the orbits of nearby stars and gas clouds. By studying these motions, astronomers can infer the presence of a spinning black hole and estimate its mass and spin. The rotation of Kerr black holes shapes the behavior of accretion disks, structures of gas and dust spiraling into the black hole. The frame dragging effect causes these disks to align with the black hole's spin, creating observable features. The collision and merger of Kerr black holes generate gravitational waves, ripples in spacetime that propagate outward. These waves carry information about the black hole's masses and spins, providing insights into their nature. Instruments like LIGO and Virgo have detected gravitational waves from black hole mergers, confirming the existence of rotating black holes. The spin of Kerr black holes influences the waveform of the emitted gravitational waves, revealing details about their rotation and interaction.